Hi everybody, welcome back to Chem 140. Just winding the music down here real quick. Alright. We're going to finish Unit 10 today. We're going to get started on Unit 11. Unit 10 is the last of the units that we need to cover for our next quiz, which is Units 9 and 10. So once we have finished that today, I will put the quiz up for the next set. And then we're going to work on Unit 11. Unit 11 has its own quiz, which is how much stuff is in Unit 11. But we are going to go through it fairly quickly, because there's not that many things to really cover. It's just there's a lot that I can test you on. So there may be 2 quizzes due next week. I don't know. Probably not. But if you're wondering, like, well, wait a second, there's like 9 quizzes in this class. We've only done 4, and it's week 7. Don't worry, they're kind of like piled up towards the end, so we will get to them. But do worry a little bit, because there will be a lot of quizzes all of a sudden. So that is just kind of an unfortunate side effect of the design of the course. But we'll do the best that we can. We left off on Tuesday last week drawing simple Lewis structures with this sort of connect the dots mentality. And as the molecules get bigger, we start to find that it gets cumbersome to do it this way. Like, it doesn't really work after a while. Is there a better way? There is. I just read the screen and I realized I didn't mention the lab number 3. Lab number 3 is due tomorrow. The closing date is Wednesday. Get it in by the deadline, please. So what we're going to do for our Lewis structures is, instead of using this connect the dots approach, we're going to trash that and use a new approach. We're going to use this 5-step plan approach to drawing Lewis structures in a more organized way that will work for a much larger number of Lewis structures. And by much larger, I mean virtually all of them. All the ones that we're going to do in this class, anyway. So the connect the dots method does still work, but this method will save you a lot of time for more complex structures. So let's go over our plan here. So the first step that we're going to do is we're going to count the number of valence electrons in any atom contributed to the molecule. So if I write down CO2, I'm going to look up how many valence electrons carbon has, and then how many oxygen has, and then how many the other oxygen has. And that information comes from the periodic table. Remember that the group number tells us how many valence electrons are available, and the valence electrons are what participate in bonding, so those are the ones that we're going to use. The second step is that we're going to try and establish some sort of framework. We're going to take our atoms and we're going to arrange them on our paper in a way that makes logical sense. Something needs to be connected in the center to everything else, and that atom is going to be the one that's listed first. So this is important to note. There is an exception. If H is the first element, use the second element as the central atom, because H can't be a central element. H will only bond to one thing. Now, what if you have a formula like C2H4? If you have a C2H4 type situation where you have multiple first atoms, those atoms should go in the center, as centrally as possible, and then everything else should be arranged around it, most likely in an arrangement that is symmetrical. So for C2H4, you'd put 2 H's on each side. For C2H6, you'd put 3 H's on each side, and so on. Oh, sorry, I had to yawn there. Those first 2 steps are a little nebulous, and when we actually do examples with this is going to make more sense. But I want to just go through the motions here, just so you can see what all these steps are before we start using them. When you have connected your atoms to your framework, you're going to start withdrawing electrons from the total that you calculated in step 1. The bonds that you draw to connect them cost electrons, From what's left over, you're going to just fill in octets. You start on the outside atoms, and then you put them on the central atom if there's anything left over. Now, in some cases, you will be electron deficient. You will not have enough electrons to give everything an octet. If that's the case, then what you're going to do is you're going to start making multiple bonds to the central atom by swapping out non-bonding pairs for bonds. And we're going to show an example of this. Oh, goodness. In just a second. Sorry, it's 2:30. I don't know what it is about 2:30, but it makes me tired. All right. So these are the 5 steps. We're going to illustrate a diagram of a Lewis structure and then refer to these steps in each step of the way. But if you are doing a Lewis structure using this strategy and at any point everything has an octet, stop where you're at and you can skip all the remaining steps. Now, some important caveats for these steps. Is that you must do them in order. Ignore the fact that my pen glitched out there. And that you cannot backtrack. So if you skip a step for any reason because you can't do anything at that step, you can never return to it. Don't go back and try and do it again. Like, oh, I moved some electrons for bonds. Now I'm going to draw more electrons for octets or something. So once you skip a step, you must move on to the next step. You do not ever go back. And you have to do them in order. I realize those are more or less the same description, but to some people they may not be. So, all right, what we're going to do is we're going to do carbon dioxide. So let me get this set up real quick. There we go. Sorry, I'm sitting here yawning, and I just wanted to not yawn into the mic, so I had to mute it there real quick. All right, so here's our example. We're going to do CO2. So at the top there, you can see that step 1 is to count all the valence electrons. So let's start by doing that. How many valence electrons does carbon have? If you go to the periodic table and you see what group it's in group 14. That means that it has 4 valence electrons. We're going to add that to how many valence electrons each oxygen has. It's in group 16, so that would be 6 valence electrons, and there are 2 of them. And so we'll just indicate that there. What is the total number of valence electrons? It'd be 4 plus 2 times 6, or 16. So we're going to have 16 electrons for our valence pool. We must use all these electrons. You can't ditch any extra, and this is all you get. So you cannot add extra electrons. So if you are drawing your Lewis structure and you use 18 electrons, and you ask me, hey, what's wrong? I didn't get the right structure. The first thing I always do is count your electrons. Because oddly enough, when it comes to matters of counting, I think students are the worst at counting. And it's not just students, instructors are too. I am so bad at counting, you guys. Like, if you ask me to count to 20, I will miscount it like 2 or 3 times before I actually do it right. So, be as meticulous as you can. And if you're going to fuck up, this is the place you're going to do it, with the counting. So, like, the chemistry isn't so bad. I think everybody can do the 5 steps here, but it's the counting. It's the goddamn counting. Like, that's where we're going to mess up. So, try and be careful with that. If you have to focus a little bit and not make a mistake, you don't want to mess up on the counting. Because then when we go to the next step, which is draw a framework and start using our electrons, we're going to immediately rely on set counting. So here's my framework. I'm going to put the C in the middle because it was the element listed first. I'm going to put the O's around it. Now, where I put them doesn't really matter, because what I'm going to then do is I'm going to connect them with bonds. And we haven't talked about molecule geometry yet. We're going to do that in 161, so put them wherever you want to. I arrange them kind of as symmetrically as possible, because that's, generally speaking, going to be the shape that we're going to see. And for the purposes of this class, that's fine. Now, bonds contain electrons, so each bond that we added costs 2 electrons. So I need to withdraw those from the total. So I'm going to go -4, and now I have 12 left, because I used 2 for each bond. So don't forget to subtract your electrons for the bonds you draw in the framework step, because they count towards that total. The next thing you're going to do, I need to flip to the next slide real quick. All right. So we haven't gotten to step 5 yet. That just appeared in my box that I've got there. There we go. All right, step 3 is going to be put electrons around the outer atoms. Our goal is to complete the octet. We don't need to do one per side. We're just going to do this. 1, 2, 3, 4, 5, 6. So completing the octet on this oxygen cost me 6. And now I'm going to do the same thing with the other outer atom. 1, 2, 3, 4, 5, 6. So I've used all the electrons at this point. If you use up all the electrons, you do have to stop writing electrons. We cannot just keep adding them because we can't go above this number, remember. Step 4 is put leftover electrons on our central atom. Well, we don't have any left over, so we're forced to skip step 4. We're going to go straight to step 5. You'll notice that step 5 only really applies if you ran out of electrons for the central atom. In this case, we did. If I check my octets here, I see that this has an octet and this has an octet, but this carbon only has 1, 2, 3, 4 electrons. It doesn't have an octet. In fact, it's not even close. So what we need to do is we need to start using some of these non-bonding electrons on the sides here to make multiple bonds. So I'm going to do this. I'm going to take this pair of electrons, and it's going to become a bond. That doesn't change the octet because I've just moved those 2 electrons from the left over here. Now they're in this bond. And remember, they're shared, so I get to count them. But it does help carbon get closer to an octet. Now I have 6 here. So what do you think I should do? Well, I'm going to do the same thing on the other side. For this class, just as symmetrical as possible is our goal. Now if I do that and I count valence electrons on carbon around this central atom, I get 1, 2, 3, 4, 5, 6, 7, 8, and I do satisfy the octet. And so that means that the Lewis structure for CO2 would be something that looks like this. And there you go. I'm just tidying up after. All right. So now that you've seen CO2 get constructed, these next few slides just go over that. I just did this example, so I want you to try this with ammonia. Ammonia is pretty simple. You could do this with just connect the dots, but what I want you to do is apply these rules. I'm going to give you 3 or so minutes to try this, and then I'll just hit the spacebar and reveal the structure. And we'll go through it stepwise to show how we got that. Okay, I'll see you in a bit. Let me know if you have any questions. One more minute, we'll go over the answer. All right, I'm going to reveal the answer because it should just pop up on the screen here. And then let's go through the process just to see how this worked. So first we're going to count valence electrons. And you should have got this, 8. And then I'm going to just draw my hydrogens around here. You can put them in any orientation you want to. And then I'm going to connect them, so that's 2, 4, 6 electrons. And then I'm going to fill outer octets. Well, all my hydrogens are on the outside, so they just need a bond or 2 valence electrons, and they're good. So I'm going to then go to step 4, which is put the remaining electrons on the central atom. And if it doesn't complete its octet, then we would make multiple bonds. But it did complete the octet, so this is the correct structure. Then I would tidy up. Generally speaking, when you tidy up your structure, make everything right angles for this class, and you'll be okay. In 161, we're going to learn that we don't want to draw everything with right angles. But for 140, that's fine. We're not going to go into geometry because we just don't have time to cover that topic. All right, I'm going to give you a bunch of these. And I want you to try... Oops, that's not what I meant to do, sorry. I'm going to give you a bunch of these, and what I want you to do is try using the 5-step approach to draw all of these structures. Now, you do need to draw all the electrons, which means that any electrons that are on outer atoms must be shown in your picture. So don't just draw in only the atoms and the bonds. Make sure that you are putting in all the non-bonding pairs. They do have a purpose, and that purpose will be discussed in 161 when we talk about geometry. Okay, so try that for these molecules. I'm going to give you about, because there are a lot of these, I'm going to give you like 7 or 8 minutes to do this, as many as you can, and then we'll go over, I'll probably just do all of them, so. All right, I'll see you in a bit. Let's do about 2 more minutes, and then we'll go over the answers. All right, let's go over the answers here. We need to do that on this screen, though. All right. I put CS2 in here because it is the same molecule as CO2. So I'm not going to do that example other than to just write the letter S over this O here. So if I do this, I still get the same number of electrons, and I still get the same structure as CO2. And it turns out that that's sort of a shortcut that you can do once you get really proficient at writing these structures. Is if you just count the electrons, it corresponds to a specific shape, and the atoms will always conform to that. So whether I used carbon and sulfur, or carbon and oxygen, or even something like silicon and selenium, if they're all in the same columns, you get the same result. They have the same geometry. So that's kind of neat. We could just skip that over. Let's do PCl3. And if I count the number of valence electrons, what I get is this. Should be 26 available electrons. And so let's draw our structure here. So I'm going to go P, Cl, Cl, Cl. First, we're going to connect these three. So that's 3 bonds, which is 6 electrons. And I'm going to do valence electrons around the outside. So 2, 4, 6, 10, 12, 14, 16, 18. So everything on the outside has an octet. I do have leftover electrons. They go on the central atom. Do I need to make multiple bonds? No, everything has an octet. So I've used all the electrons. Everything has the octet rule satisfied. Should look like this. And if you want to tidy up, you can make these straight lines so that they're right angles, but this is good enough for me. Let's do the same thing over here. 28 plus 4 is 32. So we'll make our framework. 4 bonds is 8 electrons, so I have 24 electrons left to play with. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And I've run out of electrons, but everything has an octet, so I will just stop right there, and there's my structure. And it looks like that. All right, moving on to CH2O. You'll notice I have a bunch of different atoms now. We just do the same thing, sum them all together. So 4 plus 2 is 6, plus 6 is 12. And I'm just going to put C in the middle and put the rest of them around the outside. Go 2, 4, 6. And then H's don't need electrons. 8, 10, 12. There you go. Except carbon here does not have an octet. I only have 6 valence electrons around carbon, so I'm going to remove these from my oxygen and then add them to the bond to make a double bond. And there's the Lewis structure for CH2O, also known as formaldehyde. This is what you embalm stuff with, or preserve tissue, or clean surgical equipment with, that sort of thing. All right, let's go on to C2F2. And let's see here. 8 plus 14 is 22. Is that right? 4 times 2 is 8. 14 is 22. Yeah, that's right. Okay. All right. I'm going to put the central atoms next to each other, and then I'm going to symmetrically arrange the other ones around the outside. So I'm going to stick an F on both sides. I'm just going to do this. 2, 4, 6. Then we'll do outer octets. 2, 4, 6, 8, 10, 12. And now we have 2 central atoms, so I'm going to just try and make them like this. So that one has an octet. However, I ran out of electrons here, so I have none left. And this carbon right here does not have an octet. So what I need to do is I need to share electrons. Now here I have a choice. I could use fluorine or carbon, but since I want the result to be symmetrical for the purposes of this class, I'm going to just take them from here, and I'm going to do that. And there's your structure. So I don't want to make a double bond of fluorine here because I would have to share lots and lots of electrons, and I would have carbon looking like this. So, for instance, maybe I did this instead. So we'll draw fluorine real quick. And so maybe you were like, oh, why can't I do this? Remember those guidelines that I told you about where carbon likes to make 4 bonds and fluorine likes to make 1 bond? And generally speaking, it's 8 minus the 1's digit of the group number is how many bonds they make. This structure at the bottom here doesn't follow that. So fluorine should only make 1 bond. And all carbon should make 4 bonds, according to those guidelines. Not everything will follow those guidelines, but if you have the opportunity to follow the guidelines, you should. This structure has shown carbon made 4 bonds and all of my fluorines made 1 bond. And so everything works out for those guidelines. So if you have multiple options, which you will as these structures get more complicated, refer back to those guidelines. Everything should have an octet, but if there's multiple ways to make that octet that satisfy the rules, pick the one that follows the guidelines of how many bonds something should form. And so that's why this is the right structure, and we're never going to speak of this structure again. I ran out of space, so I got to go back to the top now. So we're going to just erase everything. So pause the video if you don't have that, because it's gone now. And we'll do C2H6. And that looks like 14. And I'm going to connect the two in the middle here. 2, 4, 6, 8, 10, 12, and then 14 is actually the two in the middle, and everything is done already. Like, on step 2, we were finished. So that one's great. And then finally this one. Remember, C is the central atom, so we're going to arrange everything around it. Can't really make this symmetrical along a horizontal axis, but that's okay. Maybe symmetrical around... oh, this would be the horizontal axis. Can't be symmetrical around the vertical one. So this is 2 bonds, which is 4. Then we'll make outer octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's our electrons. They're all accounted for. Who do I make more bonds to my carbon? Remember, bromine only wants to make 1 bond, right? Nitrogen wants to make 3 bonds. And so I'm going to just erase 2 of these non-bonding pairs to turn it into 2 more bonds to give carbon its octet. And this is the correct structure. All right, I hope that has helped illustrate how to do Lewis structures. It's kind of difficult to write quiz questions around these, so what you're going to have to do is you're going to have to draw a Lewis structure on your paper, and then based on the structure that you drew, provide answers on Canvas to the questions that I ask you. So I might ask you to draw a certain structure and then tell me how many bonds are there total, or how many double bonds, or how many triple bonds, or whatever. All right. That is it for chapter 10. So hooray! Oh, we get a hooray. So we'll turn that music on. All right. Give me just a second to boot up the chapter 11 slides here. So screen will go blank. It already did go blank, actually. And where are my slides? There they are. We'll get that started up here. I do not want to pick up where I left off because that was the end of the slides. We want to start at the start of the slides. There we go. All right. Unit 11 is kind of the turning point for 140. In my opinion, this is a professional opinion, I feel like the hardest parts of Chem 140 are like units 2 and 3, because you're getting in here with some understanding of algebra and math, and then I tear it all apart by making you do sig figs on everything. And then you have to do dimensional analysis and word problems, and no math class makes you do word problems. Everybody skips the word problems, right? So those parts are particularly challenging. And then you get to like units 5 and 6, which are like temperature and matter and stuff like that. And we hit the easy part of the class. And now that we're done with this drawing structures and understanding the basics of chemistry, we're going to start getting to more of the in-depth and detailed stuff. This is where the class starts to get more difficult. So if you've been at cruising altitude for this class, expect to put in a little bit more work from this point forward, because these sections tend to be more complex and more difficult. Unit 11 has its own quiz. Unit 12, I believe, also has its own quiz. And I think there's a 13-14 quiz, and then there's a 15-16 quiz. Or maybe there's just a 15. I don't know. I mean, I know. I had to go look it up. I don't have it memorized because I can look that up later. So yeah, we're going to try and keep up the same pace that we've been doing for this class, which is fairly fast, I would say. So if you get stuck or if you have questions, please let me know about those. There's not much I can do in 5 minutes, though, because we are coming up on break time. So I'm going to say let's take our break now. And when we get back, we'll just jump right into Chapter 11. So let's put this on the screen. And we'll get more Zelda Wave starting here. everybody had a nice break. I sort of zoned out. I was watching the feed window, and it has a different timer in it that's a little behind, and then I saw this one turn red, and I was like, oh, why did it do that? Oh, because I didn't hit the button. Whoops. All right, so we're back. I have enough water for the last hour here. Unit 11 is all about nomenclature. Nomenclature is the systematic method by which we name substances. So we're not going to just refer to compounds in this class by letters of their elements and just reading them off. So no more NaCl. We're going to call it sodium chloride because that's what it's actually called. We're going to first categorize the compounds into the three categories you see below. So ionic, molecular, and acid. Acids are a special compound that you're going to see a bunch of. And then we're not really going to talk about what makes them do stuff until Chem 163. But it's very important in both a chemical sense, like these are the things that acids are capable of, and also a biological sense, because acids are abundant in the environment, as are bases, and they have different consequences on biology and physiology. So we're going to start by just naming acids and letting you have that information handy so that you can pull it out when you need it. All right, so let's go ahead and get started here. Oops, maybe not. Here, I got to click over here. All right. The first rule of nomenclature is that you need to know what category the thing that you are trying to name falls into. The second rule, I guess, would be you don't talk about nomenclature or something, or some sort of Fight Club reference, whatever, I don't know. Because all of the rules are unique, it should be very straightforward for you to just apply the correct set of rules to whatever it is you're doing. But the rules are unique, but only subtly so. So if you use the wrong rule set, you get a slightly wrong answer. But as far as we're concerned, if it's slightly wrong, it's still wrong. So be very careful here. Make sure you are applying the correct rule set. And so in order to make sure that you can do that, you have to first identify what category does your substance belong to. Is it ionic, is it molecular, or is it an acid? At this point, you should know the difference between ionic and molecular just by looking at the substance. Look for ions, which means metals or ammonium. If you don't see those, it must be molecular. But what's an acid? We'll describe that right here. These are the things that we're going to name. The first two sort of go into the same category because they're both ionic and they follow the ionic rules. But the other ones have their own different sets of rules. So we've got ionic rules for the ionic compounds. We've got molecular compounds, which will follow different rules. And then finally, acids follow their own set of rules that are a little bit more convoluted. Oh, I might have to sneeze. Sorry, just a second. I thought I was going to sneeze, but I did not. Okay. When I use the word binary, what I mean is that there are two elements. Only two elements. Not necessarily two atoms, so I could have a bunch of atoms of the same element in my compound. But binary just means that there are only two atoms or two elements in our formula. One of them will be a metal and one of them will be a nonmetal in order for it to be ionic. Polyatomic ionic compounds just have a polyatomic ion somewhere in there, or maybe they are only polyatomic ions. That's possible too. Binary molecular are any molecular compound or covalent that has only two elements in them. They'll both have to be nonmetals for that to work. And then finally, what is an acid? An acid starts with H in the formula. That's because that H will fall off and become H+ as an ion. Acids are sort of the midpoint between binary molecular and binary ionic. They're this strange gray area that does its own sort of unique thing, and the H+ just pops off, and then the H+ reacts with other stuff. Now, not all things with H that come first are acids. The most obvious example I can think of is water. Water follows the covalent, binary covalent rule set, or binary molecular. So we'll come across those exceptions as we get to them. Water is really going to be the only one. I'm not going to test you on water because it's abundant. We're going to test you on other esoteric stuff so that you can apply the rules correctly. So what I want you to do, is I want you to categorize each of these compounds. One of them is a ionic compound. One of them is a covalent compound, and the other one's an acid. I want you to tell me which one is which in the chat because it's way too quiet in the chat. So I'll give you 1 or 2 minutes to do that. So go ahead and do that, and we'll go over the answers in a second. All right, let's go over the answers here. So acids are easiest to identify. Just find the one that has H in front, right? So there we go. We got that one. Then let's look for metals or polyatomic ions. So here's my metal. So this must be my ionic. And that leaves this last one to be covalent. That should be a V. It looks like an R. There we go. How do you know if something is metal or non-metal in the transition metals? All the transition metals are metals. For our purposes. So gold, silver, platinum, chromium, titanium, etc. All of those in the middle chunk of the periodic table, we're going to treat them all as metals. And the reason for that is because remember that where the metal non-metal staircase is, it's kind of pushed over to the right side. Everything on the left of the staircase is a metal. That includes all the lanthanoids and actinoids. Those are also metals. All right. I got more of them. These are more complex. Oops, I didn't mean to do that. So, same deal. Just testing your knowledge here. So, we'll number them here. 1, 2, 3, 4, 5, 6, 7. Same thing. Tell me which category each of them falls into. We'll go over the answers in about 2 or 3 minutes. All right, one more minute. We'll go over the answers. All right. We're going to take the same approach to doing this. So the first thing I'm going to do is let's find all the H's in the front. So there's one and there's one. So those must be acids. That's easy enough, right? Then we want to find all the metals and all of... Oops, I didn't mean to change the color of the pen. I want that, and then I want highlighter, and then I want that. Okay, there we go. Let's find all the metals. So here's a metal, here's a metal, here's a metal. But remember that an ionic compound can also contain polyatomic ions, right? Of which ammonium is also a polyatomic ion. So even though there's only non-metals in this, ammonium is an ion because it's on the list of polyatomic ions. So we got to include that one too. That's how I get you, right? And then whatever's left over is covalent. So number 3 probably tripped up most people. That's why I put it here where it's 0 stakes. So be careful. Don't make that mistake again. All right. You now know how to categorize compounds. Now what we're going to do is we're going to discuss the rules by which we name each of these compounds. We're going to start with ionic, and then we're going to do covalent, and we're going to do acids. We're probably only going to get through ionic today. In the... How much time do we have left? 40 minutes. We might be able to do ionic and covalent. We can't finish all of them, though. That's okay, because I don't want 2 quizzes due on the same day anyway, so... All right. This is the rule for naming an ionic compound, and it looks a lot simpler than it is. It's deceptively simple, but once you understand the nuances, it is simple. Okay? You're going to drop names in the box and then do what the box tells you. So for name the metal, you just find whatever metal you are naming and drop it in the box. For name the non-metal with "ide," you're going to append "ide" to the end of the element so that it sounds nice. What does it mean? What do I mean by it sounds nice? We have a systematic way of chopping off letters and adding "ide" to things. So you might have heard of chloride versus chlorine. What's the difference? We're going to talk about that. So let's talk about the metal. Metals are just the names off the periodic table, and if that was all there was to this, I would not have this much white space after it, right? When you name a metal, we need to examine what ions it forms. And if the ion it forms is consistently the same one over and over and over, for example, things like sodium or potassium always become these charges. Where's my pen? There it is. So, for example, this always becomes this. There is no other charge for sodium in an ionic compound. Same with, say, calcium. It always becomes this. Or aluminum. Aluminum is always this. Because those elements follow the octet rule, right? We pitch their valence electrons until they have an octet from the previous sublayer or subshell. And then the charge that we observe is the charge we always get for an ionic compound for these elements. If this is the case, you just use the metal name by itself. And the reason for that is the charge is fixed. We don't need to include the charge in the name. So for sodium, you would just write sodium. For aluminum, you just write aluminum. For the purposes of this class, these are the ones that I'm going to call fixed charges. You may have seen on the online text or other various sources that there is a set of elements in the middle of the periodic table that has a fixed charge, and they look like this. And they make this sort of staircase. And for our purposes, the only one of those that you need to know is aluminum. I don't care if you know that gallium or zinc or cadmium or silver are always fixed charges. For our purposes, you just need to know that aluminum belongs to this group. The rest of them you can name without the charge indicated, or you can indicate the charge. It's up to you. But for aluminum, do not put a charge after aluminum in the name. And what I mean by that is this next step. So I'm going to clear the screen real quick. If your element is not one of these fixed charge elements, then what we call it is a variable charge element. A variable charge element needs to have its charge indicated, and the way that we do that is we use Roman numerals. Now, in case you don't know the Roman numerals from 1 to 10, I'm going to write them out on the screen for you. I just need to switch over to this so you can see that. All right, so we're going to write out the Roman numerals here. Roman numerals are only used in 3 places, as far as I'm aware. The 3 main ones, I should say. The first is the Super Bowl, which happened yesterday. I heard that the Rams won. I had forgotten. Then I saw that the Bengals were involved, and I was like, what? Okay. That must have been a crazy-ass bracket. The other place that we use Roman numerals is Final Fantasy games. What are we up to, like 15 now? 16 is in the works. I've been following that a little bit. And then the third place that we use Roman numerals is naming metals that have variable charges. So that's where this comes in. The Arabic system of numbering is the numbering scale that we use. It's base 10. The Roman system of numbering is far more dumb. It uses base 5 question mark? Not really. Actually, you know, I'm not going to put the little things on the top and the bottom. I'm just going to number them like this. So 1 is just I, and then 2 is I. 3 is I. And then 4 is IV. 5 is V. 6 is VI. 7 is VII. 8 is VIII. And then we have IX for 9, and then X for 10. And then it keeps going. So like 50 is L, 100 is C, 500 is D, and then 1,000 is M, and I don't know what goes past that. And so to write a number, you just get a bunch of these letters all written together. And this is dumb, and this is why the Roman civilization fell. Didn't have anything to do with Julius Caesar trying to like reach too far. It was entirely the Roman numbering system. No, everybody hated it. I'm totally making that up. I have no idea what their thoughts on this were. But we use Roman numerals for charges for naming ionic compounds, so it behooves us to know it. You're really only ever going to see up to 8, but I list up to 10 because why stop at 8? Like, might as well just finish off the last 2. All right. Now, the charge has to be indicated to you in some way, or it has to be solved for you to be able to name it properly. So if I had a compound like, say, this, so if I had FeCl3, you would have to solve for the charge on iron. We know that each chlorine is -1, and there are 3 of them, right? So that means that this iron must be +3, so its name would be iron 3. All right. And you could do this for the charge on any element that is a variable charge metal, as we have shown here. There's some examples at the bottom. Now, very, very, very important. I would only preface this with 3 varies if it wasn't something that was going to involve you. And the question I'm going to ask is, how do you format names for Canvas? Okay. This is worth writing down and having handy because every quarter students mess this up because Canvas is super picky. And I go back and look at the answers and I say, I can't give you points for this because you didn't format it correctly. Okay. So this is a warning. This is not a threat. This is a warning. If you don't follow this format, Canvas will mark it wrong because Canvas is expecting you to type in the names how they are supposed to be done. So I'm going to write an example here for iron 3. All right. Rule number 1. Elements are not proper nouns. Do not capitalize them. If you do, it will be marked wrong and I will just shrug. Okay? Do not capitalize element names. Never, ever, ever in Canvas. If you are writing a sentence and the first word of your sentence is an element, then you do capitalize it. So you might say, iron is a common metal found in the earth. In that case, you would capitalize iron. But if you wrote, the bars of metal are made of iron, you would not capitalize the iron, okay? So do not capitalize iron, because elements are not proper nouns. All right. Number 2. Involves this gap right here between iron and the parentheses. Do not enter a space between the element name and the parentheses. The only space that you should add should be between element names themselves. So, for example, if I was naming this iron 3 and then chloride, you'd have a space between your name and then the next name. But within the name itself, do not put a space between the iron and the parenthesis for the Roman numerals. And then finally, number 3, the Roman numerals use capital letters. Okay? So you do not capitalize the iron, but you do capitalize the 3. So that would be iron parentheses, capital I, capital I, capital I, close parentheses. Do you include spaces and formulas? No. A formula is one contiguous. So like if you were typing in Canvas, like say C2H5, you would enter that as this. No spaces. If you add extraneous characters, Canvas does mark things wrong. And then you get no credit for it. Okay? Be very careful. So this is your warning, okay? Make sure that you follow these format rules for Canvas when you're typing in names, because these are the actual rules. If you wrote this on paper and you capitalize iron, I would be like, whatever, I don't care. I would comment on it. I say elements are not proper nouns, but I wouldn't take points off. Canvas will take off points, and I'm not going to go in and edit all of the answers because you did that. Now, why can't I just tell it to not be case sensitive? And the answer is that the only real option that I have for that is to check a box that allows you to make typos, and it considers capitalization a typo. And depending on the formatting of the word that is involved, I do or I do not check that box. For instance, it controls how many keystrokes you can make a mistake for. So, for example, if your word that you were typing in was fluorine, this is how you spell fluorine, but you typed in this. See the mistake here. If I told Canvas, okay, I want you to be able to make 2 mistakes. So the first mistake would be I delete the letter O. And then the second mistake would be I insert the letter O in this space. So this would be one mistake, 2 mistakes. So typically I try and tell Canvas, okay, allow 2 mistakes. It's called the Levenshtein distance or something like that, which you can look up on Wikipedia. I had to read all about this. Now, the issue with some words is that if I do that for, say, iron 3, and I say you can make 2 mistakes, and you enter this, then what Canvas thinks is that, okay, for mistake number 1, you deleted this, and it says that's within 2 mistakes, and it gives you credit. That's obviously wrong. Iron 3 and iron 2 are not the same thing. So when I have those sorts of things involved, I tell it, you cannot make any typos. And if your typo was instead this, where you entered a capital letter, it says, oh, that's 1 mistake. I allowed 0, and it calls it wrong. Okay? Same with a space. If you added in an extra space, it says, okay, you have 1 mistake from the expected answer, and it will mark it wrong. So that's why these rules need to be very strictly followed, is because Canvas is programmed in a very specific way, and the only alternative I have is to type in every possible conceivable answer I can think of that you might make. And that's not really feasible because I don't know how many spaces you'll enter, for example, or I don't know which letters you'll capitalize, or if any, or all of them, or maybe you put in square brackets instead of curly brackets for one or both, and there's just too many options. Like to program that would literally take me an infinite amount of time because there's an infinite number of ways you could write it. There are also an infinite number of typos. So my expectation for you on Canvas is to follow these 3 ground rules when writing anything in for the naming section. And I do warn you at the beginning of the quiz, don't capitalize elements and don't put extraneous spaces or parentheses unless you are supposed to. Okay? If you deviate from these rules, you do so at your own peril. Because 99% certainty it will mark your answer wrong, and then I just have to shrug because I can't give you credit for it because I have warned you. Okay? So be meticulous. Be very careful. All right. We've learned how to name metals. Remember how I said it looks simple, but there's a lot more involved here? We just spent 10 minutes naming a metal, right? Which one of the steps is find your periodic table and read it. But there's a lot more to it than that. All right. Now we're going to do nonmetals. Nonmetals follow the same sort of Canvas rules. Don't capitalize them and don't typo them. There are no Roman numerals for the nonmetals. Roman numerals are only for metals with variable charges. So we don't have to worry about that here, at least. But what we do have to worry about is spelling and making sure that you tack on "ide" to the correct chunk. What does "ide" mean? "Ide" means that the element that you're looking at is actually an anion. So, for instance, chlorine is spelled normally, but chloride is spelled with "ide" because of the negative charge on it. So there is a difference between these two things. And if you called your compound chlorine when you intend to do chloride, Canvas will get upset with you. It will say, oh, I expected 0 mistakes, but you made 2, and mark it wrong. That's by design. I want you to spell this correctly. All right. So with that in mind, we'll go back to this slide really quickly because I need to write out all the ides for you, the ides of chemistry. It's like the Ides of March, but probably worse, right? Sorry, I'm just clearing the screen here. Actually, no, I want to do this. There we go. Boop. And then we'll go over here. All right. So the elements that I care about, I got to get my periodic table out here for this, are these elements. I'm going to include arsenic in here, even though it's not super common. All right. These are the elements that will have ides in them. And then I'm going to add down here H also. And so the ions that we form, we'll write out for these. So I believe these are listed in your text somewhere. I misspelled it already. I'm going to screw everybody up. But I have no idea what table these are in or where they are. And you do stuff like this. Nitride, phosphide, arsenide. Oxygen is oxide. Sulfur is sulfide. And again, you've probably heard these before. Maybe not selenide. And then for the last few, we've got fluoride. Be careful of that U, it comes first. You don't want flouride, you want fluoride. Cl- is chloride. There is an H in chlorine, it's silent, because English is silly. And then we got bromide. And then iodide. And there you go. I'm going to include hydride in here because it is a thing that exists. However, it is rare. More often than not, you're not going to see H as H minus. You're going to see it as H plus because H plus is for acids. And H plus actually has a different name. We're going to talk about it in the acids part. Actually, we're not going to talk about it in this class. We're going to talk about it in 163. But in case you're curious, H plus isn't really found on its own in a solution. It attaches to water, and so we call it hydronium, which is H3O plus. And we'll talk about that in 163. All right, let me get the periodic table off the keyboard so I can type again. But there's your ides. So now you know the name of all the ides that we're going to see in this class, and pretty much everywhere else. Note that carbide is a name, but carbide is not actually on this list. I will include carbide for you in case you were curious. Carbide is a polyatomic ion. And what it is not this. So this is not carbide. In fact, for the longest time, I thought carbide was just C with a 4- charge. Like, literal years of teaching later. And then we got into the lab, and there was calcium carbide. And I saw that the formula was CaC2. And I was like, huh? How? And I looked it up, and it turns out carbide is C2 with a 2-. If you're curious, its Lewis structure looks like this. What do you attach on those ends? You put H pluses, and then it's neutral, and you get acetylene. So, just some random chemistry factoids, I guess. So, let's actually name some ionic compounds before we run out of time here, because we only have like 15 minutes left. But all right, so now we're just going to follow the rules from our box here. So, name the metal, name the nonmetal with ide. So, whatever this is, we would just name it. So, you go look it up, and you write its name down. Again, don't capitalize. Is it a fixed or variable charge? Well, potassium always forms this ion, right? So we do not need Roman numerals. Again, if you do this, Canvas will mark it wrong because it's not expecting that. So be mindful of that. Don't put in parentheses unless it is a variable charge. And then what is this? This is bromine, but we use the ide form. And so the name of this would be potassium bromide. All right, I'm going to give you another one, and I want you to name this in the chat, and I'll give you about a minute to do it. So go ahead and try that. Type it into the best of your ability of what you think you should type into Canvas. Again, no capital letters. You'll notice that I used a capital letter right here because this is the start of a sentence. Notice that this one is not capitalized, okay? So this should not be capitalized, but because I'm typing sentences, PowerPoint formats it automatically. So just be careful, okay? And I'll give you 30 seconds to name it, although you've already started. So. All right, so let's name it. So what metal is this? I've already screwed it up. I can't spell. If you can't spell, this is a challenging part of the class. I can spell, but I make a lot of mistakes when I'm typing. And I just live and die by the delete key. Now, there's an answer in the chat here that brings up an interesting point. So you put in disodium oxide there, which unfortunately is incorrect. But the intuition that you have of, well, what do I do with this 2, is actually a good intuition. That 2 should do something, right? However, if we go back to these rules here, there's nothing that says anything about numbers of how many elements there are. It's literally just name the metal and name the nonmetal. So we ignore the numbers for the coefficients. So no dis, no tris, no tetras. You're just going to name the metal and the nonmetal with ide. Okay? So literally interpret the directions as shown for this section. That said, keep in mind that your first instinct was to put di on it, because when we get to non-metal naming stuff, you do that. And that's where everybody screws this up, is they mix up the rules. So be careful, because Canvas would not accept disodium oxide because it's incorrect. It's good that you were thinking that, though, because you're thinking ahead. And that allows me to say, like, this is where people will make mistakes, is because the rules are very similar. And when we name covalent compounds, we're going to put dis and tris and tetras everywhere. So, all right. So now let's put it all together. Let's suppose that you had an ionic compound and you knew it contained these two ions. The first thing that I want you to do is I want you to put these together into a formula and tell me what that formula is. And then I want you to tell me its name. So type the formula to the best of your ability in the chat and then name the compound that forms. And I'll give you 2 minutes. All right. Let's go over the answers here. So making the formula should be very straightforward, because we're just going to balance out the charges, right? If I get another one of these, it'll go together. But if I look at this element and I look at it on the periodic table, is it an element that has a fixed charge? I.e., does it follow the octet rule because it falls in one of the columns that allows it to do that, which is groups 1, 2, or 13. 13 being aluminum. And the answer is no. Cobalt is in the middle of the periodic table. It's like right next to iron or something, right? Yeah. So this is a variable charge metal, which means that when I name it, I need to give it its name with parentheses and the Roman numerals. And then when I name this, I name it with "ide." And that's what we get. So this is the name of the compound. It's cobalt 2 chloride. There you go. All right, I'm going to give you another one. So make the formula out of it, and then tell me what you would call it. Remember, for the metal, if you don't know if it's fixed or variable, look at your periodic table and tell me what group it is in. If it's in the groups that follow the octet rule, you don't need to put parentheses charge. But if it's not in one of those groups, you do have to include the charge as Roman numerals. All right, I'll give you 2 minutes, and we'll check back in just a bit. All right, let's go over the answer here. So the formula, again, real simple to put those two together because they have the same charge. But then you got to look up what this is. And it's not magnesium. It's manganese. And manganese is in the transition metals, so we're going to include its charge as Roman numerals. And then this oxygen would be oxide. So there's our name and a formula. All right, I think I have a bunch of these. Yeah, so I have lots of these, but we're going to run out of time before we can go over them. So what I'm going to do is I'm going to put these on the screen for a few seconds, and you could pause the video here if you want to copy these down. And then I'm going to go put the next set on the screen here. And so you can pause the video here and copy these down if you'd like to try these. What we're going to do is when we come back tomorrow, we're going to start on this slide. I'm just going to jump right into doing the exercises. And then we'll finish Unit 11, the rest of it tomorrow, because this is ironically the hardest part. It seems simple, but really just getting into the swing of doing this is the hard part of naming. Once you get into the mindset of, okay, I have to interpret these rules literally. I cannot deviate from these rules in any intuitive way. I just do what it tells me to. Then this is no problem. The problem is going to be resisting the urge to like put something in where you think it should go, but it doesn't explicitly say to do that, or getting the rules mixed up, because these rules will be similar to the covalent rules, and it's very easy to mix those up. All right. So there was page 1, there was page 2. We'll do polyatomic later. That's where we're going to leave it. So I'm going to put this back up on the screen. I do want to thank everybody for coming out to the lecture. Let me know if you have any questions. I'm going to go and put quiz 5 up, which is chapters 9 and 10. That'll be due a week from today. Lab worksheet number 3 is due on Tuesday, but that can be turned in on Wednesday as well, before it closes. Thanks again for coming out to the lecture. Let me know if you have any questions in the Discord or by email. Take care, and I'll see you tomorrow.